good morning, good afternoon, and good evening to everyone who's tuning in. Hope you're doing well and staying safe. On behalf of BioPetro, Arab Oil and Gas Academy, SPE Egypt section, I'd like to welcome you all for our first session in the Introduction to GIS and Spatial Data Visualization course. I am Mayar Tarek, a third-year gas and petrochemical engineer student at Alexandria University, and I'll be your moderator for today. Before we start, please, I'd like to remind you to drop your questions in the Q&A section below. Please keep the chat box professional and ethical. I just want to note that our course will consist of 4 webinars and a quiz after each webinar, so please don't forget to submit your quizzes before the deadline. Now let us give a warm welcome to Dr. Tarek Kandakji, who will be giving us a session in the definition and introduction to GIS. Dr. Tarek is emerging academic with PhD in geosciences and demonstrated track record in conducting research in multidisciplinary environments such as international NGOs and universities. Areas of expertise include environmental science, earth science, ecology, atmosphere, air quality, water quality, geomorphology, hydrology, environmental health, land management, and land conservation. Strengths include geospatial analysis and modeling, GIS, remote sensing, and data analysis. Currently, Dr. Tarek is working as a GIS coordinator at the city of Lubbock in Lubbock, Texas. Dr. Tarek, thank you so much for coming, and the mic is yours.
Thank you, Mayar, for the wonderful introduction, and thank you, Dr. Al-Garhi, for allowing us to share our experience with young youth and the people in all over the world. It's very valuable to share knowledge, and this is really one of the values of learning and sharing knowledge between people. And again, thank you, Mayar, for your wonderful introduction. I'm very happy.
My honor. Thank you, Doctor.
Thank you. The honor is mine.
Honor.
And as one of the questions here, some people asked if they want to know how this will help them in their career. From now forward, you will see how this GIS is very important aspect in any environment, because in any field of study, it provides you with, it answers the question of where. This is one of the main reasons of GIS, answering the question of where. And it can be applied in many fields, as we will see from now on as we go with the slides. So my seminar or my presentation today going to be about giving introduction to GIS. What is GIS? Why we use it? And what are the terms? How the data is structured in a GIS mode? Now, to start, let me see, I can move the slides. Okay, in this course, we will cover these 4 topics. The first lecture today going to be definition and introduction to GIS. The second lecture, which is going to be tomorrow, by God's willing, it's going to be types and components of maps. What are the maps? What are they composed of? How, what type of maps? How you present your data in a map? What the map should include and what should not be included in a map. What's the question that the maps answer? The third lecture going to be the projection system and data sources, and you will have a lot of fun and you will have a lot of surprises in the projection system lecture, because we have a lot of information about maps and GIS that are basically wrong or misleading. So you will see the third, I'm excited about the third lecture because it's very important and you'll have a lot of fun in it. The last lecture is about spatial analysis and visualization. Once you build a solid understanding of the main components of GIS, then you are ready to see how the GIS will help you in visualizing your data, your spatial data. Spatial data are basically data with geographic coordinates, so that will help you to visualize your data in a very beautiful way and informative way. The first lecture, as I said, definition and introduction to GIS. What is GIS? Let's start with this question. What is GIS? Many people have definition for GIS. Like if you Googled it, what's GIS, you'll have a lot of definitions. But the main definitions I'm going to use is the one that's defined by the United States Geological Survey, USGS. They have their own definition of GIS, which also similar to all the other definitions. According to USGS, GIS is a computer system that analyzes and displays geographically referenced information. It uses data that's attached to a unique location. If you look at the definition in the slide here, you see it's composed of main concepts: a computer system, analyze and displays of geographic data, and the data has a unique location. Those are the three main components of GIS definition. And by the way, there we have GIS, which is Geographic Information System, and we have GIS, which is Geographic Information Science. It's very important to know the difference between both. They both have GIS. You can use GIS as an acronym. But the Geographic Information System is the tool that we use in geographic information. It's the software, it's the hardware, all the components, or the computer system. It's how you show your data and analyze it. While GIS science, Geographic Information Science, is the science of geographic information. It means that the theory behind the theory behind coordinates, like all the mathematical algorithms used, the statistical methodologies used, like the science is broader concept than system. So when we say GIS system, Geographic Information System, we are more focused and oriented towards the computer system that helps us in visualizing and analyzing our geographically coordinated data. So in the definition, the computer system includes hardware. We should have a hardware like computer or a supercomputer or any type of hardware. A software, you need to have a platform that will help you deal with your data. And in GIS, with the development of technology, the better the hardware and the software, the better your analysis will be and the faster your analysis will be. So we will see in the history of GIS how the software is developed in a way that will be synchronized with the technology development. The other component is data sets. Like you need a data set. You need to have something to work on, whether it's a Excel sheet, CSV, whatever information you have, you need to have a data set that is geographically referenced. It has a geographic location, a known geographic location. Any data without geographic location is just data. But when it's associated with coordinate system or something that identify location, then it becomes geographic data. Then you have the people or the end users, the people who use the technology, the people who apply the analysis, the people who make use of the data, like the end users, for example. Like you make a map for a reason. Like let's say you are working for the government. Let's say the government of Egypt. You want to show them the map of the roads and of the highways in Egypt. Then the government and you are considered the people because you utilize the information you have. And then you need to have methodologies and procedures. You need to adapt a certain pathway for your data. Like, what do you want from this data? What's the answer you want from these data? What's the question? So each map has a purpose. It fulfills a certain purpose. In order for the map to be informative as much as possible, you have to understand the purpose and you need to fit that map to answer your question. That's being said, we have functions for GIS. So what are the functions of GIS? First of all, first function is to capture data. Like the way of capturing data is different from person to person, from organization to organization, from field to field. Like some data are available online. Like you just capture the data from going online and download the data. Some of the data you need to go to the field with the GPS unit and just start recording data. That's also a way of capturing information. You can also you can have a notebook and go to a certain location. Like let's say you went to an oil field, for example. You want to map oil fields in Egypt. You take a GPS unit, you go to select a certain location. Let's say you have a certain area that you want to know how many oil fields or oil drills are there. You go there with a GPS unit, you record the X and Y coordinates for that specific oil field, and you can add some notes like it's surrounded by agricultural areas, it's abandoned, the consumption of that oil field is such and such. So you can associate your information, the location data you have, with other information. That's called capturing. Now, storing the data. Like when you have the data captured, you want to save it. GIS allows you, the computer system in GIS allows you to store that data in a specific format that you can use specifically for GIS. Because the information you store, it's not only data, it has locations. And we will see in a while about the file format for GIS and what it contains. Now, the third function of GIS is editing or manipulating the data. It's very important. This is very important part of GIS functions, and it actually opens the door for all the other functions. And this is where you need to know what's the purpose of your map, because you may have raw data. For example, you have a population of each governorate in Egypt. Like let's say you have a shapefile, or you have a map, or have data, a table that contains all the governorates in Egypt, like Cairo, Al Giza, all those governorates, and you have the population associated with each one. But you want to submit to the let's say Ministry of Interior Affairs, the ministry, the government of Egypt wants to know the population density in each governorate. So what to do? You have only information that contains population and the area of each governorate, like the area of Cairo, the area of Giza, and you have the population. So what you do, you manipulate the data. You add a new field that explains the population density. You divide population by area, and there you are. There you have it. You edited the data to show the population density. This is also part of the fourth function, which is the query. And once you have the data here, you can visualize it in any way you want, and in any aspect. So you can change the data, as I said. Like let's say, in another way of manipulating the data, you have a road map of certain area, and you want, let's say, to see what kind of houses or agricultural areas coming through these roads. Like these roads, what are they interfering with? You can do the analysis by querying these data, which is the fourth function of GIS, the query. The query is when you look for data, for what you want. After you edited and manipulated the data, now you need to find what you want. Like let's say in our population and population density example, you want to know the governorates with a high population density. Like you set the threshold, like you say, if the population density is more than this, then I'll consider it high. Then you do a query analysis and see where those governorates, what are those governorates? Or you want to see what governorate in Egypt has more oil fields than others. You do a query. Then you do analysis. You perform analysis. Like for example, in this area with high population density, you want, let's say, see where the people are concentrated, like in this governorate, where the people are concentrated, in what area. Let's say you have Cairo, you found that Cairo has the higher population density. So you want to know where the people of Cairo are concentrated. You want to know the income, like what's the income range, like what neighborhood has the highest income, what neighborhood has the lowest income, like if you want for public assistance or something. So you do analyze, you do analysis of this data you captured and edited and manipulated and queried. And of course, manipulation here, we talk about the good way of manipulation. By the way, maps do lie sometimes. You can lie with maps, and we will see that later in the projection system. And as we go further with the lecture, you see that some people can lie with maps. Now, the last function of GIS is displaying your data, which is one of the very important aspects. It's like you make a good food, a very delicious food, but the representation of your food is not good. People will not like it. Like if you have very wonderful, like Mayar said, mulukhiyya, like you have wonderful, you made wonderful mulukhiyya, but the representation of that food is not good, then people will not have a good perspective of that item. Same thing goes for maps. If the display of your map, display of your data is not good, then people will not benefit from that map. So display is very important. How you arrange the layers, how you present the information. Do you have a lot of redundant information? Do you have less information than you should have there? It all in part of the display. This is the one of the most important aspects. So these are the functions of GIS. It's very important to know and absorb these functions. Now, the history of GIS. This is my friends is Roger Tomlinson. Tomlinson is the father of GIS. He developed what's called the Canadian Geographic Information System, CGIS. It's the first operational GIS. He made it usually for land use database, like for natural management, like what type of land use we have. So they needed to answer that question, like what's the land use of certain part of Canada? So Tomlinson came and gave them this tool, the CGIS, and he became since then the father of GIS. That doesn't mean, by the way, that maps were not available before, but he's the father of the GIS system as a software, as a computer system. Later on, Harvard developed what's called synergistic mapping, SciMap. SciMap, it as I said, developed by Harvard University. It shows capabilities of using computer to make maps. They applied more tools. They developed it a little bit more. And later on, people got interested in maps and building software. So we've seen a lot of industry because people saw potential, like mapping is becoming a very important topic in almost all fields, and we will see later on how. So the most notable GIS software so far is introduced by Esri, the Environmental Systems Research Institute. Esri is one of the big companies, big industries in GIS. Like we have a lot of other free softwares, like QGIS and Tableau and all that stuff. But GIS became pioneer in geographic information system software. And I never seen any software that's most user-friendly than Esri. The first product of Esri was ArcInfo. It was developed in the 70s. Basically, it was kind of a coding system. It was compatible with the technology back then. Windows was not invented in 1970s. Macintosh was not invented in 1970s. And so ArcInfo was very much synchronized with that technology in the 1970s. Then, as technology in software advances, we have now we have Windows, we have Apple, Mac, all that stuff. So Esri introduced ArcView in the 1990s. It has more friendly user interface, where you have icons, you have you need to click on that icon, you have a button for a certain function. So it became very easy and very friendly, and they developed a lot of tool sets and help sessions to allow customers to build experience in using GIS. Now, in summer of 2000, Esri introduced ArcGIS, which is used until now. ArcGIS is the most user-friendly software. It has a very good library of help documents, and it's widely used. It's very common among all GIS users. Again, you have to pay for it. It's expensive. It's not cheap. But if you're affiliated with a university or you're affiliated with NGO, you can have, if you're a university student and your university is having partnership with Esri, you can get a license for free. Or if you're affiliated with NGO, you can have it for a low price, like a special price. Of course, there are and by the way, ArcGIS is going to be the software we're going to use in these seminars to demonstrate some data. So, but there are free softwares like QGIS and other softwares. They are very good in dealing with data, but those builds for certain function, and it's kind of the user interface is not as friendly as ArcGIS. Of course, ArcGIS is still used till now. But the next step for Esri is to produce Arc Pro. And by the way, ArcGIS is composed of many packages, like you have Arc Desktop, Arc Catalog, Arc Scene, etc. Like ArcGIS is a package of softwares associated with it. And now Esri want to produce, or they already introduced Arc Pro, which is more user-friendly, more associated with current technology, and it eventually going to replace ArcGIS. Now ArcGIS reached version 10, and they want to replace it with Arc Pro, and they will stop supporting ArcGIS. Who use GIS? This will answer one of the questions in the somebody asked before. Why it's important? ArcGIS is useful in almost all fields, including but not limited to education. You map your students, where your students are coming from, because students coming from different parts of the country. So you need to know where are your students coming from, what kind of difficulties they face. When you have a map of your students and their location, you can help in developing the education system. Health, you need to know what's the nearest hospital. Like if you have a certain hospital that's serving a big area, you need to know what is that area. Do we need another hospital? How we are gonna bring patients from remote areas? So health is very important aspect. Petroleum engineering is very like a field that use GIS a lot. Like you map the oil fields. You have radar, like you have radar images of the fields. Let's say you have information about the capacity of each oil field or the production expected from each oil field. You can map them and visualize them. Environment, of course, it's very important. Like you need to map drought. You need to map, let's say, areas subjected to climate change. You can put them in the map, like temperature. What areas is suffering from high temperature or low temperature, precipitation, etc. Retail, like when you do retail, you need to know where the houses are located. Let's say the pricey houses, where are the pricey houses is located? Like if you have a certain budget and you using a map for retail, you say, okay, like this area is where I need to buy because this area has houses that fits my budget. Let's go there, and it will help you make decision in buying a house, for example. And the real estate, sorry, this is real estate aspect, not retail. I talked about real estate in terms of the houses. Now for the retail, like you see the big franchise like McDonald's, Popeyes, all those big places, how they decide where they want to build their restaurants. They use GIS, like they use multiple layers of GIS, like decide, okay, this location is the best. It has the lowest like affordable renting for our agency. It has population, like all that information. And in insurance, for example, like if you, for flood zone areas, if your house is located in an area that's mapped to be high flood zone, then your insurance will be high, etc. And all that thing. Manufacturing, public safety, sustainability, telecommunications, like the maps of the telecom towers, electric and gas utilities, how the electric system is mapped, natural resources, government water, like a lot of applications. To my knowledge, I don't think there's any field that does not make use or potentially can make use of GIS. You tell me your field, and I'm going to definitely tell you how you're going to use GIS in that field. Now, in addition to that, there are geospatial technology. Geospatial technology is a term used to describe the range of modern tools contributing to the geographic mapping and analysis of Earth and human societies. So, and you can see that geospatial technology is involved in our life parts, especially with the development of portable devices. So the first, or one of the geospatial technologies is Geographic Information System, GIS, the one we're doing right now. It's part of geospatial technology. Remote sensing, which is satellite images or aerial images. It's very important part of geospatial technology. And by the way, the advanced countries, the countries that has very strong military power, like the United States, Russia, China, all those have a very strong geospatial technology in terms of GIS and remote sensing. And in fact, GIS and remote sensing is some people say it was developed in the military and later on it was allowed to be used by public, because it helps you to identify your enemy and know the weak points and the strength points of your enemy. You can see your like, let's say you have a very powerful satellite, you can monitor a country of interest based on that satellite. So based on these images, remote sensing images. So it's very important and very advanced and very serious technology. Global positioning system, GPS, it's part of geospatial technologies. So in our life, there are thousands of applications for these three geospatial technologies. They can interact in multiple ways. You can use a single one of them, or you can multiply them all, combine them all in a single application. Like, let's say the GPS in your cell phone. And as I said, the advancement in portable devices technology allowed us more to have geospatial technology in our life. Like your cell phone has a GPS. You go from point A to point B. Then you can see, you can change the background from a map of the roads to a satellite map and see the surroundings. So we have tons of applications for geospatial technology in our life, and we are reaching a point where we can't live without it. Now, who cannot live without GPS in his cell phone to tell them where to go? I myself use it a lot, especially when I travel. Like in the United States, I travel between states for the first time in my life. How can I do it? I just put my phone on my car and I put the GPS and say from point A to point B. And you have the luxury to choose many roads, many options. Like, okay, I don't like to drive in a highway. I'd like to drive in countryside roads. I choose that route. Like the geospatial technology is magnificent, and it involves in our life in many aspects. Now, let's go deeper in GIS. GIS data models. Like, what is the data we have in GIS? The real world data we see in our life, the locations of stuff, the all the applications like the houses, the roads, all those are data. How we can put these data in GIS? This is done by understanding the data models. So we have two data models, vectors and rasters. The vectors is the geometric shape of the data, which is could be a point, a single point, or a line, or a polygon. And each point has X and Y coordinates. So the basic form of vector is a point. You need to remember that term, vector and raster. Vector is the basic form of it is a point, like you have a single point with X and Y coordinates. Now, let's say you have 2 points connected to each other with a line, like you're connecting point A and point B. Then you have a line. But when those lines are enclosed, it's called polygon. Polygon is any shape, any enclosed shape, a triangle, a square, trapezoid, like you name it. Like once the points are close to each other, like the first point is connected to the last point, or one point is connected to the other point, to one of the points, then you have polygon. Now, in lines and polygons, the points, as we said, the basic component is a point. So once you have a line or polygon, that point, that single point, is called a vertex or vertices. And so when we say vertices, that means we are meaning a point in a line, like part of a line or part of a polygon. The other data model is raster, which is the grid cells. These are square cells arranged in each other with having certain values to form eventually an image. It's raster, for when you take a picture with your phone and you zoom in, like let's say you have that picture on your computer and you zoom in, you will see small squares. That's a raster. Like the raster is anything that composed of grid cells. And each cell covers a certain area on the ground. Like this cell, when we're talking about GIS, like here, for example, in this map here, like you have this cell, it covers a certain area on the ground. And the size of the cell is called resolution. The bigger the cell, the smaller the details you can see. Like let's say you have a farm beside a road, beside like let's say a residential area. If you have a pixel that covers all, you cannot see these details. But if you have smaller pixels, you can identify, okay, this is the house, this is the farm, this is the street, this is the residential area, etc. Here's another example of this is the real world, how we model the raster, the difference between raster and vector. So this is a real world image, and this is the source. You can see the source of the image here. Like you have a river, you have a forest, you have a house. This is how it looks in a vector. When you want to transfer this real world image to a vector, this is how it's going to look like. This is a line representing the river, like a point, you draw that point and you have a river. Here, the forests, you have a forest as a polygon, like an area here, or you have the house as a one point, a single point. In raster model, you see many pixels are representing those areas. Instead of points, you have pixels. Now, once we're done with the models, we need to know what's the feature type. The feature type is the layer we put, or the, like once you, for each vertex, let's say in here, I'm going to back a little bit here to the vector, the point, or let me go back to this one. Here, each one is a feature, like this is a feature. This is a feature. This is a feature. Now you can combine those two in a single feature. But let's say now this one is a feature with an S name, a feature named S. Here, maybe let's say small forest. And this feature is big forest, for example. And this feature is a river. So the set of information, or the set of shapes with a certain category, is called a feature. Now, what type of feature we have? We have two types of feature. We have discrete features and continuous feature. I'm going to talk about the difference between them now. Discrete features, you have a definite boundary for each. Like this feature, you say, has a certain cutoff point. It does not, it's not mixed with other points. and relates to a specific geographic location. Now, these points, these features can be point, like let's say oil fields or oil wells, rivers, parcel map. You have a parcel of that piece of land. It's defined by a certain boundary. You have a land use map, like you have a map of several land use of Egypt, let's say. This is each polygon represents a certain land map, or maybe a raster, each set of pixels representing a certain land cover, and it does not mix with the other categories or with the other parts of that feature. And we're going to say a little bit how the difference. Now, continuous feature, the feature is faded in itself. Like when you look, do you know the rainbow? When it rains, you look at the rainbow, it composed of colors. The colors are faded in each other. There's no specific boundary. There's no visible specific boundary between each color in the rainbow. It's kind of faded within each other. So that's why discrete feature. It has a location, discrete location, like approximate location, no gaps between cells. The output map usually show range of values. And for example, the temperature map, rainfall map, and we're going to see an example here. Let's look at these maps. Here, the land use land cover of Egypt, let's say. This is composed of polygons, or maybe a raster here. Each pixel has a certain code, whether it's a barren or cropland or etc. So each pixel has a specific category, and there's a distinct differentiation. Like you can say that this is cropland, and this is, for example, irrigated cropland, and this is barren land. There is a boundary between those classes. Similar thing for governorates. Like let's see, this is a governorate areas of Egypt. Each governorate has its own polygon. It's not discrete. It's indefinite. You have a certain boundaries. Now let's look for the rainfall maps here. This is a rainfall map, a vector map of rainfall. There are its classes, like this range here is 0 to 5 millimeter. Now, you don't know, there's no cutoff edge between those categories, and it's kind of continuous. There's no specific borders. Like, for example, this heat map here, like the heat, the colors, the classes are faded in. There's no visible or specific edge between the one category and the other, or one temperature and the other. Similar here, like it's range of data. It's discrete location, not specific. And there's no gaps. It's all continuous. Everything, the whole feature is continuous. Here, you can see gaps. Like let's say, for example, these regions are not mapped. Nobody knows what this region is, what kind of land use in this region. So you can't have this gap in continuous data. Now, how to apply GIS functions? As I said, GIS assume the real world is presented by either a point, or a line, or a polygon, or a surface, or imagery, satellite imagery, as you can see here from the images beside me. Now, each feature in GIS is called a layer. Each feature is called a layer. Now, layers can be assembled either over each other. They can overlay. You can put, like, let's say, the governorate maps. You can put on top of it the city maps, the city points, like each city has a point, and you can put that point on top of the governorate, so you can see that city in what governorate it's located. And you can put land use map. You can overlay them, stack them over each other to see what kind of information you can have. The vector, by the way, vector feature file format is called shapefile. Now, the shapefile .shp, it doesn't come as a single file. Like if I want to give you the shapefile of Egypt, I don't give you just one single file. It's composed of many files. The file for projection system, where, like how you define the projection, a file for the data stored in it, and we will see later on how these files are structured. But you need to know for now that the vector, the shapefile is the file format for a vector. Now, each layer or each shapefile or each vector has a attribute table, like you have a table associated with that feature. We're going to see it a little bit in the software. Now, the rows in that attribute table are records, like each row is a record here. Now, columns represent information, like what kind of information presented for that record, for that point. Like, let's say this is the cities in Egypt. This is Cairo. This is Giza. This is Alexandria, etc. So each point or each location here is associated with a certain city, and it has the information, the shape. What's the shape? It has a specific ID field. So each attribute table must have a unique ID field to identify that location, because you might have two cities, like in the United States, there's a city called Egypt in Houston, a small city or a small part of Houston is called Egypt. Now you have multiple names. You confuse that between Egypt the country or Egypt the city. When you have an object field, you have a unique ID, like, okay, I'm going to give that a code of 0. I'm going to give that a code of 1. You need to have a unique ID, and this is default. ArcGIS creates the object ID, or sometimes it's called the FID, and it's unique for each feature. It cannot be replicated. And also, there's a shape file, which is also a default file, a default column in the attribute table. The shape, what's the shape of your data? Is it a point or it's a polygon? So those information comes in the attribute table, and we will see that demonstrated later on. Now, there are differences in the attribute table structure between raster and vector data models. The vector data models has a row for each feature, a record for each feature in a shapefile. But a raster, it has a count of features that share the same, a count of pixels that shares the same value. Like if you have, let's say, a land use map, a raster land use map, like for Egypt, for example, and each pixel is associated with a specific land use. The attribute table for that raster is going to be the land use and the count of pixels that have that land use. So it's not like the vector. The vector, each pixel, let's say it's so you can be familiarized with the idea. Each pixel is recorded with its information, but we don't have that in GIS because rasters are represented by attribute table, where you have the count of pixels that shares the same value. Now, some vectors, especially continuous raster layers, they don't even have an attribute table. So you're stuck with the data you have without any other information rather than the symbology or that specific purpose for the map. Here's an example. Like, let's say this is the United States map here. Here's a polygon. Each state is a polygon, as you see here. Each state has an FID, a specific ID. Like, for example, Alabama has an FID of 0. Alaska FID is 1. So there's no other state has the same FID. This is the row, which is the feature for each one. And the columns are information associated. Like if you click on this one, you will see all this information. The other map here is a raster of land use map of a certain part of southern United States. You see here it's composed of pixels. Each pixel has a certain land cover type. Like this is the land cover type. And you can see here the open water land cover type has almost a million pixel, 957,000 pixel share the same value with the area of such and such. Also, the built environment, this is like different. If you have built environment, different type of build, like this is urban, industrial, etc. So each one has its own, you can combine them, but here it's not shown the specificity of that built environment. But here it's repeated because each one described a certain, like this is residential area, this is industrial area, this is governmental area, this is commercial area. So each built environment has its own, but you can combine them together and get the overall count. Like the grassland areas, this is the count of pixels that has the that specific land use type. Now, we need to understand the advantages and disadvantages of each data model, the vector and raster. Vector data, which is the point, polygons, and lines, are precise. Like you have a specific location for those, and they cover, like if it's the river, let's say, is drawn on GIS and you can actually follow it, so it's precise. It's a smaller file size. It's not big. Even sometimes if you have, like say, the map of the world, the polygons, the country's polygon, it's not big, it's not huge. You can process it faster. It's faster to load, faster to process. And each feature has a row in the attribute table. Each feature is associated with information. You can manipulate and edit that information and do analysis on it. Now, the disadvantages, it's a complex system. Sometimes it became complex. Like you have, if you have a road feature of the whole world, it's very complex. And here, continuous data in a vector can only be shown using polygons, which is not very appropriate. So if you have no choice but to show your data in your continuous data, like your temperature, in a vector, it's going to be very inconvenient. You will have to use polygons. It's very hard to deal with. And that's why continuous data are very hard to handle while dealing with vectors, and this is one of the disadvantages. Now, let's go to raster. What are the advantages? Advantages of raster, like it's a simple structure. It's suitable for imagery. Like if you have image, it's better to use raster. It's very simple, like you have pixels. That's it. All you have is pixels with values, with certain values. And then it's suitable to apply advanced spatial and statistical analysis. Raster images is one of the best features, or let's say data model, to do analysis. It's very important. You will see later on. Hopefully we can see that. I don't know if we're going to cover it, but I'll try to cover it in the last lecture to apply raster. It's kind of complicated or advanced concept in GIS. Now, the disadvantages of raster files, it's a huge file. It's a very big, it's large. It takes a long time to download. Like this, you remember the map I showed you for the land use in southwestern United States? It took a long time to download. It took a long time to be loaded on the system, and all the analysis, unfortunately, is limited to the resolution. If you have low resolution data, then your data will be good for that resolution. The higher the resolution, the better your analysis. And it's the end of my seminar, but let me go through the GIS real quick. Here's the GIS. Let me cover this for now. And so this is ArcMap. This is the environment for ArcMap. And let's say this is the Egypt boundary. This is a map of Egypt. It's a shapefile. If you click the attribute table, and let me put the attribute table here, it's one polygon because we have one feature. Now, let's say for Egypt administrative areas. Now you overload administrative areas. Let's open that attribute table. And also it's one polygon. Let me see. Okay, no, there it is. This is the Egypt point. Like there are points of certain features. Like if you say the parking, see this point is highlighted here. You highlight that point. I want to know what, let's say this point. I want to know what this point is. You select that point and you will see it's selected in here. If you look at the attribute table, if you scroll down, or you can just go to the selected features. It's here.
Dr.
It's this one.
Tarek,
Yes.
I'm sorry. You have to share your screen again because they can't see
Oh,
anything.
sorry. Okay. Let me see. Let's share. Let me share screen. Okay. What about now?
Yes,
Okay.
thank you. Thank you so much.
Okay. So, let me go back from the beginning. Let me take this. So this is how GIS work. Now let's say we have administrative border. This is Egypt. This is the administrative border of Egypt. The city borders. If you open the attribute table, you will see only one record, which is Egypt. Now we have points. Another point like this. These points. What are these? Let's open the attribute table and see. So these points are kind of point of interest. You have level crossing, you have parking spots, some name of companies. Like it's a data set of all kind of point of interest. Now let's say I want to look for something called Watania. It's not an ad, it's just an example here. You go for that point, you see it's selected in here. You can zoom to that point, and there it is. You can see where it's located. So you have many information. Like let's say I want to add data. Let's see world countries. I'm going to add the world countries map. See how it fit over Egypt. Let me take off these points, and let me change the color of Egypt to be, let me see. Let's put the color of Egypt here as green. Okay, and then put it here. So this is how you highlight a certain part of Egypt. Now let's open the world countries attribute table. This is the attribute table. See, you have all the countries and with specific FID. It's not repeated. That you can flash. Let's say we want to flash Cuba, for example. Let's go to Cuba. This is Cuba. It's located here. Let's go back to Egypt. So you can do a lot of stuff in this. Like for example, here you have the country. There could be a population field. Like let's say there is a population field here in that shapefile that tells you the population of that country, and you have the area of each country. Then you can divide population by area, and you can get the population density. Now, this is an example of a raster layer. Let's go here. This is a raster layer. It's the dust storm in Egypt. I think it's on May 26th of 2010. And there's no attribute table associated with that map. So it's very important to understand the difference between those data models and what to do with it. Now, when we go to the spatial analysis and modeling, here I'm just visualizing this information. But when we're going to go to the last lecture, which is spatial analysis and modeling, we're going to create a field here. We're going to see how we can manipulate the data. It's going to be fields with population, for example, and area. We can calculate population density. I'm going to show you that in the last lecture. But now what I wanted to show you is just a visualization as introductory to what we're doing. This is how GIS looks like. These are the layers. You can see the layers stacked over each other. Like let's say you have this image and you want to put the boundaries of Egypt on top of it. Like let's say you put this one here. See? You can change the transparency of that. Like let's go to the display, and I want it to be no transparency, just like this, 0. It's solid. Now I want to be transparent and see what's behind it. Let's set it to 50% again. So see, you can see that this is these are the borders of Egypt, and here's the satellite image. So you can see that the dust storm, the sandstorm was reached here. Let's put roadmap. Let's put the, I don't know if we have a highway. Yeah, we do have a highway. So this is the highway of Egypt. Look at what you can see here, what you can visualize, like you have a sandstorm here, dust storm. Let's turn off this one for now. And you still have the roads, like this is the dust storm coming to Egypt this way. So you can imagine that this highway was subjected to a lot of car accidents because low visibility because of the dust, and you can expect high car accidents. Like, is it in Egypt? Yes, it's in Egypt. It's within the Egyptian boundaries. So this is the introduction of how we can use GIS. And of course, in the future, we will know how to present this information in a more appealing way rather than just going through this. And by that, I conclude my lecture. And I know we have only 5 minutes. I don't know if this is going to be enough for questions. I think this is the end of my lecture. Thank you for listening. And I'm sorry I left only 5 minutes for questions. So please feel free to answer me anything you want.
Thank you, Dr. Tarek, for this super informative webinar. We are all amazed, and they are asking you if you can share this PDF on Google Classroom for them.
Sure.
And I'm sure we all benefit greatly from it. Thank you so much. And now we have question. How does cataclysmic pole shift or tectonic movement affect GIS analysis, considering the constant change in relative positioning and coordinates over time?
Okay, that's a good question, and honestly, but this geological change, the cataclysmic pole shift or tectonic movement, it happens within a long period of time. So what you can do, if you want to show this, what you can do, you can map the current location of tectonics. You have a map of that tectonic plates or the continents. And then if you have a prediction of where it was before, you can redraw that and compare the position between two. So basically, GIS is more helpful when you have data that changes in a rapid way, like a city becoming bigger, a border of a country change, for example. But for those that takes long time, you can do a time series, or you can show those in multiple images. Like you can put a map of the old model of the tectonic plates, how they were, what's the expected location 5 million years ago, and you can put it in a map. And then you can put the current location of those plates, tectonic plates, in a new map, and you can compare between them. Like for the continent image, if you ever looked at the old images of the continents, how they were before in one continent, there are maps of these. So you can map this, but you need a lot of information about the previous location. And I don't know if you can map the current movement, because I think it's very slow, but you can map it. You're not going to be able to see it in actual map because it's very minimal. But on the long run, to compare between now and a few thousand years ago, you can do it, of course. I hope this answered your question. Please let me know if it doesn't.
Thank you. And our second question, would GIS serve for correlations of strata in subsurface for oil wells?
I didn't understand the question. Can you say it again, please?
Would GIS serve for correlations of strata in subsurface for oil wells?
Uh, I don't know what's the concept he used, but if it's something that changes with time, whether in area-wise or in quantity, you can definitely map it. So, Mayar, do you know what he's talking about? Can you explain it in a better way so I can answer the question?
Uh, um,
I can help explaining
I
if you want.
okay.
So imagine if you have two wells, and these two wells has like 5 miles between them.
Mhm.
So the layers will not be identical. Maybe the earth layers will be, let's say, very thin at one of these wells. It will be bigger at the second well, or maybe it will not be shown at all. Maybe the depths will not be the same. So
Mhm.
he want to compare these layers between the two wells,
Yes,
but this is
yes,
not changed
absolutely.
with time.
Yes, absolutely. You can do it. You can absolutely do it. Let me share my screen real quick with you uh, to see you how we can do it. Like, let's say that these points, for just hypothetically, these points here in this map, let's suppose they are wells. Each one is an oil well. When you have the attribute table, if you click to if you open the attribute table, it could be categories here like the thickness of the layer, maybe the distance to the nearest well. Like, you can have these information in a field in this attribute table, and then you can do analysis. Like, you see, let's say you want to see the wells with highest layer thickness, or it's like whatever application, you can map those, and you can even categorize, like you can symbolize, like for example here, you can give a symbology, and we will see that in the spatial analysis, by the way, when you symbolize features based on values in the attribute table. Like, let's say layer with high oil fields with higher thickness will have a bigger point. You can do that. You can see that. So this will be, yes, it can definitely use in the area you said. And hopefully we can see an example of that in the last lecture. I hope this
Uh,
answers the question.
Thank you, Doctor. And our last question, does QGIS have the same visualization capabilities of ArcGIS?
To some extent, yes. QGIS is a free software, and it has some capabilities. I did not work with QGIS a lot. I worked with QGIS in certain ways, but it does not have all the functionality of Simple G. It can symbolize data in a beautiful way. I am not saying it's not. It's powerful sometimes in visualizing some data. But if you want to go in details, sometimes it's better to use ArcGIS. But if you don't have access to ArcGIS, then yeah, QGIS is good. And for most users, it can, let's say, not the same capabilities, but at least enough to present your data.
Thank you, Doctor. Thank you so much, Dr. Tarek, again for your
My
effort
pleasure.
in this
Thank you,
terrific
Mayar.
webinar.
Thank you, Mayar.
And now, to highlight, this session has been recorded and will be uploaded soon on PioPetro YouTube channel. So kindly make sure to subscribe on our channel. Wishing you a great day, stay safe, and bye.